Hi. So we've spent some time in class talking about my general VHDL design approach or philosophy, but there's really no substitute for doing. So to some extent, lab number two is by design something of a VHDL boot camp. So you will see as you dive into this, uh, not necessarily the complexity is that much higher than lab number one, but the amount of things I'm asking you to do is significantly more than lab number one. We're doing a bit of a trial by fire. We're just designing different components and making sure we get a pretty decent increased understanding of VHDL as a language. But there are a couple big conceptual things that can really trip you up in lab number two. So I wanted to connect what we were talking about in class with regards to my commandments for VHDL with what you will see specifically in this lab, and it all does directly connect together. Um, Going back to our major rules or strong suggestions or commandments for VHDL, I still think a very important one is that drawing as a necessary prerequisite step to actually coding anything in VHDL. So draw more, code less. You're not writing that many lines of code this semester, and the time spent in thinking about what your design needs to be is going to save you so much time just kind of staring at a .vhd file and not knowing what to do next. Because when you're staring at that file and you don't have a mental model of what you're wanting to do in your hardware, you do wind up, in my opinion, falling into that first flaw as well. Well, let's start writing code. Let's start falling back on what I'm comfortable doing and writing sequential programs. And that is when you fall into some of those more painful traps that take more time to get yourself out of. So for this assignment, there are only a couple of key points where I say, please draw your schematic for this module. And it should be a pretty detailed schematic when you do so, labeling things out. And we'll talk about that in a little bit here as we connect it together. But we only got to two of the four in class, and we go at different paces, and that's perfectly fine. The third one is pretty vital for this lab, much more so than lab number one. And this one is this third rule or this third thought process is that the actual primitive data type that we tend to use in VHDL when designing hardware is doing more than you think it's doing, and we have to be cognizant of that fact. And another way to very succinctly state what that rule is that this standard logic, which you're going to be seeing a lot of, right? If you haven't seen a little bit of it already, it's not the same thing as a bool. It is not a binary type. They have a lot in common, but we are attempting to model hardware here, and we need much more than just a binary type to be able to model hardware. Let me talk about what I mean by that. We do tend to think of our digital logic as being this somewhat binary ideal, at least in the model of abstraction, layer of abstraction that we tend to want to operate in. We do tend to think of our digital logic being this binary thing where we have a value corresponding to logic level 1 and we have a value corresponding to logic level 0, and we have some signal that's being generated or some circuit that's doing something, and it's generating these zeros and ones for us, right? Over, and if our x-axis is time here, this is our waveform. And similarly, ModelSim will give you that view of your circuit, right? It'll give you the ones and zeros for your input signals, for your intermediate signals in your design. But that is really a very idealized view of what's happening in hardware, right? That's our ideal of our model digital hardware. But real hardware is a lot messier than that, right? This digital logic is itself an abstraction of the underlying transistor technology or whatever implementation technology for our actual compute fabric that we have here, right? And that tends to have a lot of messy analog associated with it. And I'm not saying we're having to model analog in this class. That would be more appropriate for your circuits or your VLSI classes. But we do know at least that in reality, what we have are not those really nice just binary value 1 and binary value 0. What we do have is voltage levels, right? Voltage levels on a wire where there is some value, we can call that, V high, that corresponds to our logic level 1 in our design. And then we have some other value, which tends not to be zero point 0.0 volt. It depends. This is very dependent, but tends not to have to be zero point 0.0 volts, corresponding to our V low. And likewise, although this gets to the analog effects, it's not so clean and neat, right? There's something generating a signal, and it's maybe taking some time to transition, and it just has a lot more messy reality associated with it. That is much closer, at least, to our reality. And while we're not modeling any analog effects here in our standard logic library that we are using, um, we are attempting to recognize that there are states of our circuit that are not just binary value one and binary value zero. This is not a minor point. You will be dealing quite a bit in your looking at your model sim waveforms and wondering, why am I not getting ones and zeros back out? Why am I getting other things that aren't ones and zeros? And if you were to look at the definition of standard logic, and it's all public spec. It's all open source. You can find it in your model sim install, or you can also just find the VHDL IEEE spec online. Is that this standard logic is defined to have ones and zeros as part of its spec, but it's also defined to have multiple other states associated with it. It has undriven state. It has multiple drivers state. It has things like high impedance and low impedance and other things that we don't deal with in this class, but it's an attempt to recognize that hardware is more complicated than just binary values all connecting to each other. Think back to our data flow VHDL, where we have our concurrent signal assignments, a very common and not a beginner bug. This is something that happens to us all the time, even in people who've been doing it for years and years and years. A very common error that we make is that we have in our data flow VHDL, we have a line that says signal A is set to 1, and at some point in the future, generally not the next line, but at some point in the future, we have that same signal A set to 0. Of course, let's make sure we add our semicolons, right? You may look at that and say, well, Joe, I will never do that. That's obviously wrong, right? These are concurrent signal assignments. That'll just never happen because I have a signal and I'm going to assign it and it's going to have a 1 or a 0 and never both. You will definitely do that. It won't necessarily be that obvious that you've done it. That code could be several pages apart. It could be very subtle, the condition that triggers the effective equivalent of that line to happen. It's going to happen to you, and it's going to happen to you for the remainder of your digital VLSI or hardware design career, that you have what's referred to as multiple drivers on a signal. And again, going back to our more realistic view of what's happening, well, what does that really ultimately correspond to? We have a signal, and we're wanting to drive a logic level 1 to it. And then for that same signal, we are then, and it's not at some point in the future, right? It's concurrent signal assignments. We have basically inferred this circuit here, and we're calling that our SA. Well, what should the value of that be, right? We can think of it from our EE201 perspective of, adding the voltage levels together and all that sort of stuff. Either way, it's going to correspond to something that's neither the V high nor the V low in our equivalent analog implementation. And we're going to model that, and you're going to see it a lot as our so-called X value here. So when you see an X in your design, you've done this. You have done it somewhere, and it's subtle. And then these effects can also percolate forward, right? When I have an AND gate somewhere in my system, and one of the inputs is behaving quite properly, but one of my other inputs is not, well, then my output's also going to be, I don't know what the actual resolution function is. It's going to be bad. It's also going to be X's or something that you don't actually want in your design when you have that AND gate. What does it mean to AND 1 with some indiscriminate, not 0, not 1 value here? Whatever it is, it's not what you intended. It's not what you wanted. So those bad signals kind of propagate through the entirety of your design, and it can happen pretty quickly. Ultimately, though, in your design, you have effectively created this scenario somehow. You have multiple drivers on a signal. This does go back to point, not to belabor the point, but rule number one, that hardware description is not programming. So another common reason that you would have created this, and in lab number two, it's going to happen to you. Another common reason you would have created this scenario is because you thought of SA not as a wire in your design that you've drawn a schematic for, but instead you've thought of it as a variable in your design that you're just overwriting the variable. These are not variables, these are wires. SA at any given point in time should have a logic value of 1 or a logic value of 0. For all the concurrent signal assignments we're doing, it can't have both. That's our X case. Another common, and it's very similar type of thing, is this U, this undriven state we will have for our standard logic here. And that's the equivalent of, well, we have a wire in our design and we haven't driven it at all. We've kind of cut it off from the rest of the design. We've forgotten to initialize it. We've forgotten to ever actually set a value for it. That would then correspond to not V high nor V low, but maybe that would then correspond to that zero point 0.0 volt scenario where it's just been disconnected from the rest of the system. Those U's will also propagate throughout your design if you have things that just weren't initialized. Again, you don't think of them as variables that need to be initialized, but you can think of signals that need to have some sort of default signal assignment associated with them. Uh, Again, as you draw your schematic, you will have less and less circumstances where that is the case. And let's talk about the one schematic that is a little bit complicated in lab number two. The requirement is effectively to design by the end of lab number two a ripple carry adder design that is also capable of doing subtraction. We don't have to talk about the subtraction yet, but in terms of the design that you're doing, you'll be designing this so-called full adder block. We'll just refer to that as FA here. That is your CPRE 281 full 1-bit adder. Okay? It takes in a carry bit. We'll call that C in. And if you don't remember this, that's okay today, but this is worth a refresher. Your 381 textbook does talk about this in the appendix, but you could also just look in your 281 book or look in your old notes from 281. A 1-bit adder, right? Takes input A, 1 bit, input B, 1 bit, and a carry bit to allow us to do more complicated additions. And it calculates as a full adder both the single bit of sum, the addition result, as well as a potential carry out bit. 281 was a while back. If this isn't blindingly obvious, that's okay. You do need to review this for this lab to be successful for you. And that's a single bit of addition. That's the so-called full adder. And the design of a ripple carry adder is connecting n of these individual full adders together to basically design an n-bit adder. And that we would be doing so in this class, the least to start, using structural VHDL. We would use structural VHDL because ultimately we want to do more than just addition, and that ripple carry structure is still very helpful for us. So if we want to then say that this is FA of 0, then we have FA1 all the way up to, if we started with 0, then this would be FA of n minus 1 for an n-bit ripple carry adder, where there's ultimately a final carry out bit, which could be of some value and use to us, and then there's a sum bit for each of those individual components that we have here. And once you've built the full adder, and that shouldn't take you too long, and you'll get past that pretty quickly, there is a functionality in VHDL that allows you to say, give me n of these things, for my component mapping, for my structural port mapping. It's a so-called generate statement in VHDL. It's not a for loop in the sense that our programming languages provide us with for loops or sequential programming languages. It's more of a macro expansion. I don't want to type 32 of these things, and I can't type n of these things because n could be a simulation or synthesis time bound variable. So I'm just going to do one of them inside a generate loop. It's like a macro expansion. Give me n of these things that I have. But And as you draw this, your life is going to get a little bit easier in thinking this through. But each of those signals is really going to need some label associated with it. A common mistake, and it's okay if you do this, this is the learning opportunity in this class, is to create a signal that you called carry and to use that throughout your design. And if this was a sequential programming language, and if this was inside a for loop in your sequential programming language, first add bit 0, then add bit 1, etc., all the way up through bit n of our design here, you'd be fine. That would be a perfectly valid variable to have declared and to use that variable there. But that's not what we're doing here, right? This is concurrent hardware description that we are doing here. Bit 0, bit 1 through bit n minus 1 of our adder structure is always active. It is always doing that addition. It is taking those inputs. So we can't actually use a single signal called carry because that will be then exactly what's happening over here. You'll have carry set to a value of 1 at some point in your design, and later on you have carry set to a value of 0 in your design later on, multiple drivers on that carry signal. It's going to propagate your X's all the way through. You're going to get all X's out, and you're going to feel a little flummoxed by that. And if that's going to happen to some of you, then that's okay. I may point you back to this video. So the solution is really, as we label our diagram, we just want to make sure we have different signals associated with this. You could call this carry sub 0. It's probably going to be easier for you to define an array of signals first of n bits, and then you can use a bit slice inside that array to effectively easily declare n different carry signals. And now, yes, they both have the name carry, but they're different bits inside of a bus called carry. And that allows you to then keep a very similar structure. It allows you to generate, using that macro expansion, these n bits of our full adder without having to have multiple drivers on any given signal. That's the key gotcha in this lab that I don't want you to lose, hours over. There's enough work to be done in this lab that you'll be spending some decent hours on it. But that's the big takeaway. And if you do that schematic first, and it needs more detail than this, I haven't given all the secrets away of what that ripple carry adder needs to look like. If you do draw it in at this level of detail with the extra pieces that are needed in there, then when it comes time to do your structural mapping of these n different single bit units that you have here, you're not going to run into the problems of undriven signals or multiple drivers. But in any case, the main takeaway of that third commandment of VHDL is standard logic is not just a binary 1 and 0. So when you see a U or when you see an X in your design, for want of a better way of phrasing it, you've done something wrong. Don't ignore it. Don't imagine it'll work itself out. Go back to your diagram because you've done your diagram first, right? Go back to your diagram and see, where do I have two things with the same name? Effectively, where do I have this in my design? Because you either have this or you have the signal that's completely disconnected from the rest of your circuit. It is going to be one or the other. It won't be so obvious as this. It's going to look something more like this, where it's not that obvious that, in fact, it's an analogous case to doing exactly this in your data flow here. One final thing to keep in mind for lab number 2 is, by the end, you're doing this unit, you're taking this n-bit full adder and you're creating an adder/subtractor circuit. There's a very specific way I had in mind, and I see some creativity in the answer, and you're very welcome to do it. So we have a circuit by that point that can calculate A plus B, and I'm asking you to also then create a circuit that can optionally do A minus B. And we have to then, in order to implement this the way that I had in mind, is to think back to our CPRE 281 days and to remember, from a digital logic perspective, well, I guess this is more elementary math, A minus B is the same as A plus negative B. So in fact, I'm not asking you to build a separate subtractor. That is not that more work than is what's needed in this lab. It's not what my goal was for this lab. Your goal was to build the adder, And then I wanted to show you how you can then use that adder, or remind you that you could then use that adder to also do subtraction. To calculate a minus b, you can instead, in fact, calculate a plus negative b. And then, so that's elementary school math. But what is our 281 digital logic math is a remembrance that to calculate the inverse of a value that's represented in a binary notation, we can take the 2's complement of it, right? So our 1's complement of b is just b invert. And you'll notice that you're building an inverter in the very first step of this lab. So you can calculate the inverse of b plus 1. That's our 1's complement. To make it our 2's complement, you then could add 1. So in terms of calculating a minus b, you can do so by just using your adder and making sure the second input is in fact inverted. And then we're also adding plus 1 to it. That doesn't require 2 adders. I'm going to want you to think about that a little bit, but there's an input to this circuit that also gives us kind of a free plus 1 into our adder to be able to then calculate a minus b using just that n-bit inverter, using our full adder, our 32-bit ripple carry adder, as well as a mux to optionally do this or not. So there's going to be a single bit of control that's going to dictate whether or not you want b or b invert, and that's just going to be driving a mux. Whenever we optionally want one value, it's terrible, but whenever we optionally want one value or an alternate value, you can think of it as an if statement. That would be our mux, right? That would be I either want the value of b as my input to my adder, or I actually want the value of b inverse. And I believe the way I set that up is if you just want this, that control signal should have 0. If you just want the original b value, if you're actually wanting to do a subtraction, you're going to have a control signal that the design calls n for active low for add. That's what the n stands for. Sub, if it's 1, we're actually doing a subtraction. That would be connecting your inverter to that second input of the mux. When that value is 1, the output of this is b inverted. When the input is 0, the output of this mux is just b. That allows you to do optionally just a regular old a plus b, or to do that complement to get the a plus b. You still have to figure out how to get that plus 1 into there without adding a whole different adder. That's my thoughts on Lab 2 and how it connects to what we've been kind of learning. But again, it is a little bit of a VHDL boot camp. You're learning through practice, through a little bit of trial and error, but through just grinding out some examples and learning about how different things work in VHDL. So definitely, don't suffer in isolation on this. Collaborate with us. Let us know when you have questions or when you're struggling, and we're very happy to help as always. So good luck on lab number 2, and I look forward to seeing everyone's designs. Thanks.